Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into doors to other dimensions, into multiverses, strange lights in the sky, whispered stories of portals, and the gentle possibility that reality may be wider than it appears. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into doors to other dimensions together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here quietly unfolding the story. For as long as humans have looked at the horizon, we've imagined that somewhere beyond it, there might be a passage, a gate, a threshold, a place where the world we know gives way to something larger. In ancient myths, such passages were caves in mountains or shimmering curtains in forests. In modern imagination, they are wormholes, cosmic bridges, hidden layers of space folded just beyond our reach. Tonight, we won't rush towards spectacle. We won't assume that strange lights in the sky must be visitors, nor that every unexplained story hides a tear in reality. Instead, we'll move carefully. We'll begin with the foundations of physics, with space and time themselves. We'll ask whether the universe allows for something like a door at all, and if it does, what would that mean? What would we notice, and how would it change us? So let's begin, not with flying saucers or secret facilities, but with something simpler, the meaning of a door. When we say the word door, we usually picture wood and hinges, a frame, a threshold, something you push open to move from one room into another. It feels solid, ordinary, almost boring. But in science, when we borrow that word, we're really reaching for a metaphor. A door in physics would not be made of metal or stone. It would not creak on its hinges, it would not swing inward or outward. Instead, it would be a change in structure, a reconfiguration, a shortcut through something that usually feels continuous. To understand that, we first need to ask a quieter question. What is space? Most of the time, space feels empty and still. You move through it without thinking. You set a cup on a table, and it stays there. But over the past century, physics has taught us that space is not just emptiness. It is part of a larger fabric called spacetime, a single woven structure that includes both, where things are and when they happen. One of the most famous ideas in modern science came from Albert Einstein. In simple terms, he proposed that gravity is not a force pulling objects together like an invisible rope. Instead, gravity is the bending of space-time itself. If you place a heavy object like a star into this fabric, it curves the fabric around it. Smaller objects follow those curves. Imagine a stretched sheet. Place a heavy ball in the center and the sheet dips. Roll a marble nearby and it curves toward the ball, not because the ball reaches out, but because the surface beneath the marble is tilted. That gentle tilt is what we feel as gravity. Now here is where the idea of a door begins to shimmer faintly. If space-time can bend, perhaps under extreme conditions, it can bend so much that two distant regions come into contact. Not by travelling across the sheet, but by folding it. Like taking two faraway points on a piece of paper and pressing them together until they touch. In that image, the fold itself could be called a door. Physicists have explored mathematical solutions to Einstein's equations that describe how space-time curves, and some of those solutions suggest the possibility of bridges, Not bridges made of steel, but tunnels made of geometry. These are often called wormholes. A wormhole would not be a hole in space, but a connection between two regions of space-time that would otherwise be far apart. If such a structure existed, travelling through it would be less like crossing a vast desert and more like stepping through a hidden passage that shortens the journey. But before we let our imagination wander too far, it's important to remember that mathematics allows many structures that reality may never build. The existence of an equation does not guarantee the existence of a doorway, so perhaps we should step back even further. What if a door does not mean a tunnel at all? What if it means a change of state? Think of water. At room temperature it flows. Cool it enough and it becomes ice, solid, rigid. Heat it enough and it becomes vapor, invisible but still present. The substance is the same, but its arrangement changes. In physics, this is called a phase transition. The material remains water, yet its structure transforms. Some researchers have suggested that if something like a portal were ever possible, it might not resemble a hole punched through reality. It might be more like a phase transition in space-time itself, a region where the structure of the universe shifts subtly into a different configuration. That shift might not glow, it might not hum, it might not announce itself with a flash of light. It could be quiet, rare, subtle. And this brings us to another layer of the question. When people report strange lights in the sky, or moments of disorientation, or places that feel different, we're often tempted to leap directly to extraordinary explanations, but the scientifics approach moves in the opposite direction. It begins with known causes, atmospheric optics, human perception, instrument limitations. Only when those are exhausted does it even begin to entertain structural anomalies in space-time. So tonight, as we begin this exploration, we hold two ideas gently in our hands. First, the universe, as described by modern physics, is flexible. Space can bend. Time can stretch. Under extreme conditions, geometry can behave in ways that feel almost poetic. Second, flexibility does not imply fragility. The fabric of space-time is not casually tearing open around us. If doors exist at all, they would be rare, subtle, and governed by strict physical laws. A door, then, is not magic. It is not a glowing archway in a forest. It is a possibility arising from geometry, from curvature, from the way space and time are stitched together, and for now, that possibility remains a whisper in the mathematics. As we continue this journey, we will slowly widen the frame. If space-time can bend, perhaps it can do more than bend. Perhaps there are layers we have not yet sensed. Perhaps what feels like a single continuous universe is only one region among many. But we'll move there gradually, like stepping deeper into twilight, allowing our eyes to adjust. For now, we simply sit with the idea that a door in physics is not a thing you push open. It is a relationship between places. It is a fold in a larger fabric. And the question is not whether we can imagine such folds. The question is whether reality itself ever forms them. If a door is not made of wood or hinges, but of geometry, then geometry itself deserves a closer look. We move through 3 dimensions every day without noticing them. Length, width, height. You reach forward to pick up a cup. You step sideways to avoid a chair. You stand up. These motions feel natural because your brain evolved to navigate this familiar 3-dimensional landscape. But mathematics allows more. It is surprisingly easy to describe a 4th direction on paper. You simply add another coordinate, another number that tells you where something is. The challenge is not writing it down. The challenge is picturing it. Imagine, for a moment, a tiny creature living on the surface of a sheet of paper. This creature knows only 2 directions, forward, backward, and left, right. Upward, in our sense, does not exist in its world. If you were to lift that paper and fold it, bringing two distant points together, the creature would have no language for what you just did. From its perspective, the world would seem to behave in impossible ways. A point that was far away might suddenly touch another. Now imagine that we are the paper creatures. If additional dimensions exist, they may not be directions we can freely move through. They might be hidden, curled so tightly that we do not notice them. Physicists sometimes describe this using a simple image: a garden hose lying across a field. From far away, the hose looks like a one-dimensional line stretching from one end of the lawn to the other. But as you approach, you notice something new. The hose has thickness. You can move around its circular cross-section. There is an extra direction there, wrapped into a small loop. From a distance, that circular direction is invisible. Up close, it is undeniable. Some theories suggest that additional spatial dimensions might exist in a similar way, curled into extremely small scales, so small that ordinary particles cannot easily move through them. In certain versions of string theory, the fundamental building blocks of reality are not point-like particles, but tiny vibrating strands. These strands vibrate in patterns that determine the properties we observe: mass, charge, spin. But for the mathematics of these vibrations to remain consistent, the universe must have more than 3 spatial dimensions. Not infinite extra directions, but a specific number. In some formulations 10 dimensions of space and 1 of time, making 11 total directions woven together. Now, when we say 11 dimensions, it is tempting to imagine 10 invisible hallways branching off your bedroom, but that is not the claim. Most of these additional directions, if they exist, would be compactified, curled into shapes far smaller than atoms. Mathematicians describe these shapes with intricate geometries, sometimes compared to folded origami or twisted knots. The details are complex, but the intuition is gentle. Space might have more structure than we perceive, and if space has hidden structure, then under certain conditions, regions that appear separate in our visible dimensions might be adjacent in a higher one. Return to the sheet of paper. 2 points drawn far apart on its surface can be brought together by lifting and folding the sheet through the 3rd dimension. The 2-dimensional creature would call that event miraculous. We would call it geometry. This is the heart of the hyperspace analogy. Not magic, not violation. Simply movement through a direction the lower dimensional observer cannot access. Now let's widen the frame further. Beyond extra dimensions lies another idea, the multiverse. In some models of cosmic inflation, the rapid expansion that occurred fractions of a second after the Big Bang, the universe did not inflate uniformly. Instead, inflation may have ended in some regions while continuing in others. Each region where inflation stopped could form its own bubble universe, with its own physical constants. Picture foam forming on the surface of boiling water. Each bubble expands, collides, separates. Inside each bubble, conditions may differ slightly. Some universes might have stars that burn differently. Some might expand too quickly for galaxies to form. Some might never produce complex chemistry. In another interpretation of quantum mechanics, often called the many worlds picture, every time a quantum event has multiple possible outcomes, the universe branches, not into separate bubbles floating in space, but into parallel histories unfolding simultaneously. In this view, reality is not a single line of events, but a vast tree of alternatives. And here, once again, the idea of a door shifts. A door might not connect distant places in space. It might connect neighbouring branches of history, or adjacent bubbles in a cosmic foam, or regions separated only by a tightly curled dimension. But before the imagination runs too quickly, it is important to ground ourselves. none of these additional dimensions have been directly observed. Particle accelerators, including the Large Collider near Geneva, have searched for evidence of extra dimensions in the form of missing energy or tiny, short-lived gravitational effects. So far, no confirmed signal has appeared. Cosmic background radiation, the faint afterglow of the early universe, has been measured with extraordinary precision. While it reveals subtle patterns from inflation, it does not currently show clear evidence of collisions between bubble universes. The mathematics is elegant, the evidence remains indirect, and yet, the absence of confirmation does not collapse the possibility. It simply means that if extra dimensions exist, they are subtle. Which brings us back to our central question. If space has hidden layers, if dimensions can curl, if universes can branch, then perhaps what we call a door is not an object at all. It is a rare alignment, a region where geometry permits unusual adjacency. 2 points touching not because something broke, but because something folded. As you listen tonight, imagine space not as emptiness, but as architecture. Corridors and loops, vast expanses and tiny curls, most of it smooth and stable, some of it perhaps more intricate than we can see. And if there are folds in that architecture, they would not announce themselves with thunder. They would be quiet structural features waiting patiently in the mathematics of the cosmos. We have not yet reached anomalies in the sky or strange reports from lonely places. For now, we are simply expanding our map of what the universe might allow. Before we ask whether doors exist, we are learning how many directions the house might have. If additional dimensions widen the architecture of space, the multiverse widens the architecture of existence itself. It begins, gently enough, with a question about the early universe. According to modern cosmology, our universe underwent an extraordinary expansion in its first tiny fraction of a second. This event is known as cosmic inflation. During that brief moment, space itself expanded faster than light could travel across it. Not because anything was breaking the cosmic speed limit, but because space was stretching. Objects were not racing through space. Space itself was growing between them. Imagine drawing 2 dots on the surface of a balloon. As you inflate the balloon, the dots move apart, not because they're crawling away from one another, but because the surface between them is expanding. Inflation suggests that this expansion was not smooth and uniform everywhere. Tiny quantum fluctuations, small, unavoidable jitters at the smaller scales, were stretched to cosmic size. Those slight irregularities later became the seeds of galaxies and clusters of stars, but some versions of inflation propose something even more sweeping. Inflation might not have ended everywhere at once. In certain regions it slowed down and allowed matter and radiation to form. In other regions it continued. If that is true, then our observable universe might be just one bubble in a much larger cosmic foam. Picture a vast, endlessly expanding ocean of space-time, with pockets where inflation has settled down, each pocket forming a universe with its own properties. Inside each bubble, the laws of physics could be slightly different. The strength of gravity might vary. The mass of elementary particles might shift. The balance between expansion and contraction could tilt in subtle ways. This is sometimes called the Level 2 multiverse, though tonight we will avoid numbers and labels that might feel like technical categories. Instead, imagine neighborhoods in a vast city of universes, each built with slightly different architectural codes. Now, there is another branch of multiverse thinking that emerges not from cosmology, but from quantum mechanics. At the quantum scale, particles do not behave like tiny billiard balls. They exist in states that can only be described in terms of probability. When a quantum event occurs, such as an electron passing through a barrier or taking one path instead of another, there are multiple possible outcomes. One interpretation of quantum theory suggests that all possible outcomes occur, each in its own branch of reality. In this picture, reality is not a single thread, but a branching tree. Each decision, point, each microscopic interaction leads to a subtle divergence, not visible, not accessible, but mathematically consistent. Imagine reading a choose-your-own-adventure book where every possible storyline unfolds simultaneously, each in its own invisible volume stacked beside the others. You experience only one path, but the others exist as alternative branches. Now, before we drift too far into abstraction, it is important to pause. These ideas, bubble universes and branching histories, are interpretations. They arise from equations that have been extraordinarily successful in predicting experimental results. But the existence of other universes is not directly observed. It is inferred as a possible consequence of mathematical frameworks that otherwise describe reality with remarkable precision. The cosmic background radiation, the faint microwave glow left over from the early universe, has been mapped with extraordinary detail. Scientists have searched its patterns for signs that our bubble might have collided with another. So far, no definitive scar has been found. Particle experiments have tested quantum mechanics to extraordinary accuracy. The branching interpretation is one way to understand those results, but it is not the only one. So the multiverse remains at present a possibility, a consequence of theories that are well tested in their core predictions, but untested in their most expansive implications. Yet even as a possibility, it reshapes how we think about a door. If there are many bubble universes, then a door might mean a passage between bubbles. If there are branching histories, a door might mean a way of slipping from one branch to another. If additional dimensions exist, a door might mean stepping sideways through a direction normally curled beyond reach. But notice something important. In each case, the door is not random, it is structured, governed by geometry, energy, and strict physical constraints. The universe, as far as we can measure, is not fragile. It does not casually tear. It does not ripple open with every unusual sighting or strange report. If connections exist between regions, they would require extreme conditions, energies comparable to those found near black holes or in the earliest moments of cosmic history. This perspective helps anchor the imagination. It is one thing to say that the multiverse exists. It is another to say that travel between its regions is possible. The former is a theoretical extrapolation. The latter is a far more demanding claim. And so, as we let the idea of many universes settle in our minds, we do so without urgency. Imagine standing on a hill at night, looking at a distant city. You see countless lights, each window representing a different life unfolding behind it. You cannot step from one apartment into another without crossing physical distance. The buildings are separate, even if they share a skyline. In the same way, even if the multiverse is real, separation may be absolute. Unless, of course, geometry allows something unusual, unless spacetime itself, under rare conditions, can bend so dramatically that two otherwise distant regions touch. Which brings us slowly and carefully toward the structures that might make such contact conceivable. But before we reach tunnels or horizons, it is worth letting the vastness sink in. If reality is larger than our observable patch, if beyond the edge of our cosmic horizon lie regions forever unreachable, then even without portals, we already inhabit something grander than we can fully explore. The multiverse, in this quiet sense, is not a spectacle. It is a reminder of scale. And sometimes scale alone is enough to feel like standing before a door. By now, space has begun to feel less like emptiness and more like architecture. If there are many possible universes, if dimensions may curl quietly beyond our perception, then the next question becomes almost inevitable. How stable? How is this structure we inhabit? Earlier we described gravity not as an invisible pull, but as curvature. Massive objects shape the geometry around them. Planets follow those curves. Light bends along them. This idea came from Einstein's theory of general relativity, which can be described in one gentle sentence. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. No equations are needed tonight, just the image of a flexible fabric responding to weight. But fabrics do more than bend. Under enough tension, they stretch. Under extreme conditions, they may wrinkle or twist. The universe is not a cotton sheet, of course, yet the mathematics describing its structure allows for regions of extreme curvature. Near a neutron star, an object formed from the collapsed core of a massive star, the density becomes almost unimaginable. A single teaspoon of neutron star material would weigh billions of tons on Earth. In such places, gravity is not a gentle slope, but a steep well. Near a black hole, curvature intensifies even further. Light itself can no longer escape once it passes a certain boundary called the event horizon. That boundary is not a surface you could touch. It is a limit in space-time, a region beyond which all paths lead inward. These extreme environments reveal something important. Space-time is resilient. It can curve dramatically without tearing. It can form stable wells, whirlpools of gravity, and still remain mathematically consistent. However, certain theoretical models suggest that under very particular circumstances, geometry could do more than curve. It could connect. Before we step there, let's pause on a quieter concept sometimes described as dimensional stress. This phrase is not part of standard textbook terminology. It is more of a poetic shorthand. But it captures a real idea, that energy density influences the geometry of space-time. When enormous amounts of energy or mass are concentrated in one place, the curvature becomes extreme. If the equations of relativity are extended into speculative regimes, combined with quantum theory in ways not yet fully unified, some solutions hint at unusual topologies. Topology in this context refers to the global shape of space-time, not just how it bends locally, but how it is connected overall. Imagine a sheet of paper again. You can bend it without changing its topology. But if you glue two distant edges together, you change how the surface is connected. It becomes something new, perhaps a cylinder, perhaps a loop. In mathematics, certain solutions to Einstein's equations allow for what are sometimes called non-trivial topologies, structures where distant regions are connected through hidden pathways. These are not proven features of our universe. They are allowed shapes within the mathematics. Some researchers have wondered whether extremely energetic events, such as those in the early universe, might create temporary conditions where geometry behaves in unusual ways. During the first fraction of a second after the Big Bang, temperatures and energies were vastly higher than anything achievable in laboratories today. It is during those early moments that space-time itself may have undergone phase transitions. Just as water changes from liquid to ice when cooled, the universe may have shifted from one geometric state to another as it expanded and cooled. These transitions are not speculative inventions, they are part of standard cosmology. The forces of nature, electromagnetic, weak and strong nuclear forces, are believed to have separated from a unified state during cooling phases in the early universe. But whether space-time itself could have formed stable bridges during such transitions remains an open question. There's also another way to think about stress, one that is grounded in measurable physics. Quantum fields permeate all of space. Even what we call vacuum is not truly empty. It seethes with tiny fluctuations, momentary appearances and disappearances of particle pairs. In certain laboratory experiments, such as those involving closely spaced metal plates, subtle effects of vacuum fluctuations have been measured. These experiments show that the vacuum can behave in slightly unusual ways under constrained conditions. This does not mean that space-time is fragile. It does mean that at extremely small scales, reality is less static than it appears. Now, imagine scaling up. If energy can shape geometry, and geometry defines what paths are possible, then in principle, extreme configurations of energy might allow configurations of space-time that are rare but mathematically consistent. This is where the idea of stress points becomes metaphorically useful, not cracks in a literal sense, not weak seams ready to split, but regions where curvature becomes intense enough that the structure of space-time approaches unusual configurations. However, it is essential to ground this gently. There is currently no empirical evidence that such stress points form natural gateways between universes. Black holes, as far as we can observe, behave in accordance with established gravitational theory. They curve space, they trap light, they emit faint radiation predicted by quantum theory. But they do not appear to open shimmering corridors to distant realms, and yet the equations leave room for curiosity. If space-time can bend, if it can twist, if it can undergo transitions in its earliest history, then the possibility of rare geometric features is not logically forbidden. That is a subtle distinction, not proven, not observed, but not mathematically impossible. As you rest with this idea tonight, imagine space-time not as something brittle, but as something dynamic. A vast, smooth landscape that occasionally dips into valleys and rises into peaks. Most of it calm, most of it stable, but shaped by energy and matter in ways that can become astonishingly complex. If doors exist, they would not be accidents. They would be expressions of this geometry under extraordinary conditions. Before we ask whether such expressions have ever been witnessed, it is important to understand the strength and flexibility of the fabric itself. And in that understanding, we find something quietly reassuring. The universe, even at its most extreme, follows patterns. It curves, it evolves, it transitions. But it does so according to laws that are consistent and remarkably elegant. The house may be vast, its corridors may extend beyond sight, but its structure is not chaotic. It is deeply, almost stubbornly, ordered. If space-time can bend, and if under extraordinary conditions its geometry can become extreme, then one particular possibility begins to take shape in the mathematics. It is sometimes described as a bridge, not a bridge made of steel or stone, but a bridge made of curvature. In the early 20th century, shortly after Einstein introduced his theory of general relativity, physicists discovered that his equations allowed for unusual geometric solutions. Among them was a structure that connected two separate regions of space-time through a kind of tunnel. This theoretical structure became known as an Einstein-Rosen bridge. Later, the term wormhole entered the scientific vocabulary. The name comes from a simple analogy. Imagine an apple. A worm crawls across its surface, taking the long way from one side to the other. But if the worm tunnels straight through the apple, it arrives much faster. The tunnel is shorter than the surface path. In the same way, a wormhole would not involve moving faster than light through ordinary space. Instead, it would shorten the distance by connecting two distant points directly through the deeper geometry of space-time. Picture once more the sheet of paper. Two dots drawn far apart can be brought together by folding the paper so that the dots touch. If a tiny hole were made through the fold, a path would exist between the 2 points without crossing the surface distance. This is the heart of the wormhole idea. But here is where the calm, steady voice of physics adds an important note. The original Einstein-Rosen bridge solution describes a structure that would collapse too quickly for anything to pass through it. It is more like a fleeting mathematical feature than a stable tunnel. Later, in the late 20th century, physicists explored the concept of traversable wormholes. Wormholes that could remain open long enough for matter, or at least information, to pass through. In order for such a structure to remain stable, the equations suggest that something unusual would be required, that something is often called exotic matter. Now, exotic matter does not mean alien material or glowing crystals from science fiction. It refers to matter or energy with properties that differ from the familiar forms we encounter in daily life. Specifically, the mathematics indicates that maintaining an open wormhole would require negative energy density, regions where energy behaves in a way opposite to what we normally observe. Ordinary matter has positive energy density. It contributes to gravity in a way that curves space-time inward. Negative energy, in contrast, would curve space-time in the opposite sense, counteracting collapse. It may sound abstract, but there is a gentle experimental foothold here. In certain laboratory conditions, when two very closely spaced metal plates are placed near one another in a vacuum, measurable forces arise due to subtle quantum fluctuations. This phenomenon, known as the Casimir effect, demonstrates that the vacuum itself can exhibit unusual energy behavior under constraints. The Casimir effect does not create wormholes. It does not generate tunnels in space-time. But it shows that negative energy densities are not purely imaginary concepts. They emerge briefly and delicately in quantum physics. However, the quantities involved in such experiments are extraordinarily small. To stabilize a wormhole large enough for even a single particle to pass through would require energy conditions far beyond anything humanity has produced. So we stand at an interesting threshold. On one hand, wormholes are not inventions of fantasy writers. They arise naturally from the equations describing gravity. On the other hand, no observational evidence currently indicates that stable, traversable wormholes exist in our universe. Astronomers have searched the sky for gravitational signatures that might suggest unusual lensing effects, patterns of light bending that differ from ordinary black holes. So far, nothing definitive has emerged, and even if wormholes exist, there remains another subtlety. Would they connect 2 points within our own universe, or link entirely separate universes within a broader multiverse? The mathematics allows both possibilities in theory, but theory is a wide canvas. There is also a more recent idea that adds a quiet layer of intrigue. Some physicists have proposed a deep connection between quantum entanglement, the phenomenon where particles share correlated properties across distance, and tiny geometric bridges in space-time. This conjecture, sometimes summarized in shorthand form in scientific papers, suggests that entangled particles may be linked by microscopic wormhole-like structures, not tunnels large enough for travel, but subtle geometric connections at the smaller scales. If true, this would mean that space-time itself is interwoven with relationships that resemble bridges. But even here, caution is essential. The proposal remains theoretical. It offers a potential unification between gravity and quantum mechanics, 2 pillars of modern physics that have not yet been fully reconciled. But it does not imply that macroscopic portals are opening in forests or above oceans. So where does this leave the idea of a door? A wormhole, if it existed, would not glow or shimmer in the air. It would be a configuration of space-time curvature. Its presence would be inferred from gravitational effects, from the way light bends, from how matter moves near it. It would not feel like stepping through a curtain. It would feel perhaps like crossing an invisible boundary defined by geometry itself. And even then, it would be governed by constraints so strict that accidental passage would be extraordinarily unlikely. The universe, in its quiet discipline, does not give up shortcuts easily. As we let the image of wormholes settle into the background, notice how the idea of a door has evolved once again. It is no longer simply a metaphor. It is a possibility embedded in the mathematics of gravity. But it is a possibility surrounded by steep energetic demands and observational silence. Not forbidden, not confirmed, resting somewhere in between. And that in between space, the place where mathematics allows but nature has not yet revealed, is often where curiosity feels most alive. If wormholes are the bridges that mathematics allows, black holes are the structures we actually observe. They are not speculative. They are not inferred from abstract equations alone. We have detected their presence through the motion of stars, through gravitational waves rippling across space, and even through images of their shadow against glowing gas. Yet black holes remain in many ways mysterious. To understand them gently, imagine once more that space-time is a landscape. Most of it is gently rolling hills. A planet creates a shallow valley. A star creates a deeper well. But a black hole is not just a valley. It is a steep plunge. When a massive star exhausts its fuel, it can collapse under its own gravity. If the remaining mass is large enough, no known force can halt that collapse. The matter compresses further and further, curving space-time more and more intensely. Eventually, a boundary forms called the event horizon. This is not a physical surface like the crust of a planet. It is a limit in space-time beyond which all possible paths lead inward. Even light, which normally travels at the fastest speed allowed by nature, cannot escape once it crosses this boundary. From the outside, the event horizon is calm and silent, but mathematically, something extraordinary lies beyond. According to classical general relativity, continued collapse leads toward a point of infinite density, a singularity. A place where curvature becomes infinite, and the equations themselves break down. Whenever infinity appears in physics, it is a signal that our description is incomplete. It does not mean that nature contains literal infinities. It means that the theory being used has reached the edge of its applicability. This is where black holes become especially interesting in the context of doors. If general relativity predicts singularities, but quantum mechanics governs the smallest scales, then inside black holes the two theories must interact. Yet they are not currently unified in a complete framework. Some researchers have wondered whether singularities might be smoothed out in a deeper theory, perhaps involving additional dimensions or new geometric structures. There is also another puzzle, sometimes called the black hole information paradox. Quantum theory tells us that information is conserved. In simple terms, this detailed description of a system cannot simply vanish. Even if matter changes form, its underlying information must remain encoded somewhere. But classical black hole theory suggested that anything falling past the event horizon is lost forever, except for a few simple properties like mass and rotation. This seemed to imply that information could disappear. Over decades, physicists have debated this tension, and a growing body of theoretical work suggests that information may not be lost after all. Instead, it might be encoded in subtle ways on the surface of the black hole itself. This leads to a profound idea sometimes called the holographic principle. In ordinary life, a hologram is a two-dimensional surface that encodes a three-dimensional image. From certain angles, depth appears, even though the information is stored on a flat film. The holographic principle proposes something analogous on a cosmic scale. It suggests that the information describing a volume of space might be encoded on its boundary. In other words, the interior of a region could be fully described by data stored on its surface. This idea emerged from studying black holes and the entropy associated with their event horizons. Calculations showed that the amount of information a black hole can contain appears proportional not to its volume, but to the area of its surface. It is as if reality stores its deepest records on the edges. Now, let's pause with that image. If information is encoded on boundaries, then boundaries become meaningful structures. They're not just dividing lines, they're repositories. Some theoretical work has even suggested that spacetime itself might emerge from patterns of quantum entanglement, subtle correlations between particles separated in space. In this view, geometry is not fundamental. It arises from relationships. Imagine a vast network of connections. If those connections are arranged in certain ways, a smooth space emerges. If arranged differently, geometry could shift. This brings us back gently to the notion of bridges. A proposal in theoretical physics suggests that entangled particles may be linked by extremely tiny geometric connections. Not tunnels one could pass through, but microscopic relationships woven into spacetime's fabric. If this idea is correct, then spacetime may be far more interconnected than it appears at large scales. Black holes, then, become laboratories, not because we can experiment inside them, but because their extreme conditions test the limits of our understanding. They show us where classical descriptions falter. They hint that additional structure may exist beyond our current equations. But again, caution steadies the imagination. Black holes do not currently serve as known gateways. They do not emit travelers from distant universes. Observational data aligns closely with predictions from established gravitational theory. Gravitational waves, tiny ripples detected when black holes merge, match the patterns calculated from general relativity with remarkable precision. The shadow imaged around a supermassive black hole matches expectations of curved light paths. So while black holes may conceal deeper layers of physics, they behave exactly as predicted within known frameworks. And yet, they remind us of something important. Reality has edges. Not edges like walls, but edges where our understanding reaches its limits. At those edges, inside event horizons near singularities, at the intersection of gravity and quantum mechanics, the structure of spacetime may differ from our everyday intuition. Whether that difference allows doors is unknown, but if doors were ever to form in the geometry of the universe, they would likely be associated with extreme curvature, immense energy, and delicate balances between collapse and expansion. Not in quiet forests, not in empty fields, but in the deepest wells of cosmic structure. For now, black holes stand as silent markers. They do not open, they do not close. They simply curve spacetime so intensely that we are forced to admit the universe still holds layers we have not fully mapped. And sometimes standing before those layers is enough to feel that we are near a threshold, even if no doorway is visible. So far, a door has appeared to us as a fold, a bridge, a hidden connection written into geometry. But there is another way to imagine it. Quieter, less cinematic, and perhaps more faithful to physics. What if a door is not a tunnel at all? What if it is a change of state? In everyday life, phase, transitions are almost invisible miracles. Water becomes ice, ice becomes water, water becomes vapor. The substance remains the same, 2 hydrogen atoms bound to 1 oxygen atom, but the arrangement changes. The structure reorganizes. When water freezes, its molecules settle into a crystalline lattice. When it evaporates, they separate and move freely. The transformation is not a journey across distance. It is a shift in configuration. The early universe may have undergone similar shifts. In the first tiny fractions of a second after the Big Bang, the universe was unimaginably hot and dense. Under those conditions, forces that are now distinct may have been unified. As the universe expanded and cooled, those forces separated in a series of transitions. The electromagnetic force which governs light and electricity, and the weak nuclear force, responsible for certain forms of radioactive decay, are believed to have once been unified at high energies. As temperatures fell, symmetry broke. the force is differentiated. Symmetry breaking is a gentle but powerful concept. Imagine a perfectly round hill with a ball balanced at its top. At that highest point, all directions are equivalent. The ball has no preferred path. But once it rolls slightly, it must choose a direction. The symmetry of possibilities collapses into a specific outcome. The early universe may have behaved similarly. In a highly symmetric state, forces were unified. As cooling occurred, new structures emerged. Now imagine that space-time itself could undergo transitions, not in the sense of tearing open, but in the sense of reorganizing its geometry. Some speculative theories suggest that under extreme conditions, space-time might enter different phases, different topological configurations. Instead of a hole forming in space, there might be a temporary reconfiguration of connectivity. Think of a woven fabric. Normally its threads follow a regular pattern, but under tension, or at certain points in its weaving, threads might twist differently, creating loops or crossings that were not obvious before. A door, in this picture, is not a missing piece, it is a rearrangement. This framing has an important psychological effect. It moves us away from the image of dramatic ruptures and toward the idea of structural transitions governed by laws. Even in advanced theoretical physics, when researchers explore the possibility of topology change, the alteration of how space-time is connected, they do so within strict mathematical constraints. Not every imagined configuration is allowed. The geometry must remain consistent with quantum principles and energy conditions. There is also an intriguing idea connected to the very small scales of reality. At distances approaching what physicists call the Planck length, a scale so tiny that it is far beyond current experimental reach, space-time may not be smooth. Some models suggest it could resemble a kind of quantum foam, a restless structure, where geometry fluctuates subtly. In such models, tiny connections might form and dissolve constantly at microscopic scales. This does not mean that portals are flickering open around us. The scales involved are so small that they would not permit passage of atoms, let alone people. But it reinforces a key theme. Space-time may be dynamic even in its deepest layers. Now imagine scaling upward. If space-time can fluctuate at tiny scales, and if extreme energy conditions in the early universe allowed topological transitions, could there exist rare circumstances where larger scale reconfigurations occur? This remains speculative. But the idea of a portal as a phase transition has a certain elegance. It suggests that crossing into another region of reality would not involve breaking rules, but entering a different configuration of the same underlying fabric. It is similar to walking from liquid water into a cloud of steam. The substance remains familiar, but its behavior changes dramatically. In this framing, a door between universes would not necessarily be a glowing circle suspended in mid-air. It might be a boundary where the constants, the geometry, or the connectivity of space-time shifts. If two bubble universes formed under slightly different symmetry breakings, then their boundary, if such a boundary existed, would be a region of transition. The laws might not vanish there, they might interpolate, and here, caution remains our steady companion. There is currently no observational evidence of macroscopic topology changes occurring in our cosmic neighbourhood. The universe, on large scales, appears smooth and stable. Its expansion is gradual. Its background radiation is remarkably uniform, with tiny fluctuations that align beautifully with inflationary models. Theoretical physicists explore these possibilities because the mathematics allows them. Because the search for a unified theory of gravity and quantum mechanics suggests deeper structure may exist. But allowance is not confirmation, so as we sit with the idea of doors as phase transitions, we do so gently. A door, then, might be not a tunnel carved through space, not a crack in reality, but a shift in configuration, a reweaving of threads, a change in how distances are defined. If such shifts are possible, they would require conditions far beyond ordinary experience, energies comparable to those present near black holes or in the earliest moments of cosmic history. And yet, this framing prepares us for something important. If doors are structural transitions rather than ruptures, then anomalies, if they ever occur, would be subtle. They would not defy physics. They would express physics in rare configurations. That distinction will matter when we begin examining strange reports and unexplained phenomena. Because before we ask whether anything unusual has been seen, we must understand what unusual might look like in a universe governed by geometry. And geometry, as we have seen, is patient. It bends, it transitions, it reorganizes, but it doesn't panic. Up to this point, our journey has stayed close to geometry, curvature, topology, phase transitions, but now we begin to step towards something more familiar, reports from the sky. Over the past decades, pilots, radar operators, and military observers have described aerial phenomena that appear to move in unusual ways. Some objects are reported to accelerate rapidly, some seem to change direction abruptly, some appear to hover without visible propulsion. These reports do not prove the existence of doors to other dimensions, but they raise a question worth exploring gently. If space-time can bend, if geometry might allow rare structural transitions, what would motion look like near such a region? Before we speculate, we must ground ourselves in something simple: inertia. In everyday life, inertia is what makes your body lean backward when a car accelerates. It is the tendency of objects to resist changes in motion. If something is at rest, it prefers to remain at rest. If it is moving steadily in a straight line, it prefers to continue. This principle was described long before modern relativity. It is part of the quiet foundation of classical physics. When an aircraft turns sharply, the forces involved are immense. Pilots experience strong acceleration. Materials must withstand stress. Air around the craft compresses and forms shock waves if the speed exceeds that of sound. Reports of unidentified aerial phenomena sometimes include claims that such objects move without visible aerodynamic surfaces, make extreme turns without slowing, or produce no audible sonic boom even when travelling at high speed. It is important to approach such claims calmly. There are several conventional explanations for unusual motion reports. Optical illusions can distort perceived speed and distance. Radar artifacts can arise from sensor limitations or atmospheric effects. Perspective can compress three-dimensional motion into two-dimensional impressions that appear abrupt. The human visual system is remarkably sophisticated, but it is not infallible. Yet there remains an intriguing conceptual possibility. If an object were not fully embedded in our familiar space-time, if it were interacting with it in a partial or shifting way, then its motion might not follow the inertia rules we expect. This idea is highly speculative, but it connects to the earlier discussion of geometry. Inertia arises from the structure of space-time itself. In Einstein's framework, objects follow the straightest possible paths within curved space-time. These paths are called geodesics. A planet orbiting a star is not being pulled by an invisible force in the classical sense. It is following a curved path defined by geometry. Now imagine that an object's relationship to geometry were altered. Imagine, for instance, that instead of being fully constrained to our three large, spatial dimensions, it had access, however limited, to an additional direction. From our perspective, its path might appear discontinuous or sharply changing. But from its own perspective, it could be following a smooth trajectory through a higher dimensional curve. Return once more to the paper creature analogy. If a three-dimensional hand lifts a two-dimensional creature from one point on its surface and places it elsewhere, the creature's neighbours would observe what looks like instantaneous relocation. No path along the surface connects the two positions. Yet from the higher dimensional viewpoint, the movement is continuous. Does this analogy prove that UFOs are higher dimensional objects? No. But it illustrates how apparent violations of expected motion could arise if geometry were more layered than we perceive. There is another reported characteristic worth noting: the absence of visible propulsion. Modern aircraft rely on engines that expel mass or push against air. Rockets push exhaust backward to move forward. If an object appears to move without emitting exhaust or disturbing air, observers naturally wonder how thrust is generated. Some speculative physics proposals explore the possibility of manipulating spacetime directly, compressing space ahead of a craft and expanding it behind. In such models, the craft itself remains locally stationary while space carries it forward. This idea has appeared in theoretical studies of faster-than-light travel, sometimes called warp drive concepts. However, these concepts require enormous amounts of energy, far beyond our current capabilities, and often depend on forms of negative energy that remain theoretical. So once again, possibility does not equal implementation. It is also worth noting that modern radar systems have become increasingly sensitive. Upgrades in detection technology can reveal objects that were previously invisible. When new instruments come online, reports often increase, not necessarily because new phenomena have appeared, but because detection thresholds have changed. This introduces a sociological layer. Human interpretation is influenced by expectation. When a culture becomes more aware of certain narratives, extraterrestrial visitors, secret programs, interdimensional craft, it may interpret ambiguous stimuli within that framework. Psychologists call this a feedback loop between perception and belief. None of this dismisses reports. It contextualizes them. If doors to other dimensions existed and occasionally interacted with our spacetime, we would expect anomalies to be rare, subtle, and difficult to reproduce. Not theatrical spectacles, but edge cases. The universe, as we have seen, is governed by strict energy and curvature conditions. Large-scale geometry does not fluctuate casually, so when considering aerial phenomena, the scientifically responsible stance is one of layered explanation. First, examine atmospheric effects, then sensor artifacts, then human perception. Only after exhausting conventional explanations does one cautiously explore structural anomalies. Inertia remains a powerful guide. Objects embedded in our space-time obey its geometry. Any sustained deviation would imply new physics at scales large enough to measure. So far, no confirmed observation has demonstrated such new physics conclusively, and yet the curiosity remains. Because if geometry can fold, if dimensions can curl, if phase transitions can reorganize structure, then in principle, motion through altered geometry might look unusual, not impossible, not confirmed, but interesting. As we let this idea settle, notice that we have not leapt to conclusions. We have simply widened the conceptual space. Strange motion could arise from misperception, or from undisclosed technology, or, in the most speculative corner of theory, from interactions with deeper layers of geometry. And the only way to distinguish among them is careful, patient observation. In a universe, this vast mystery is not surprising. But mystery is not evidence of doors. It is an invitation to look more closely. When people first imagined visitors from beyond Earth, they usually pictured travellers crossing enormous distances between stars. The model was simple and familiar, one planet to another, a journey through space. But in the mid-20th century, a few researchers proposed something more unusual. What if the phenomenon was not extraterrestrial but ultra-terrestrial? Not arriving from distant solar systems, but emerging from a layer of reality adjacent to our own. This idea did not come from equations. It emerged from patterns in reports. Some investigators noticed that sightings often included behavior that seemed theatrical, elusive, or psychologically charged. Objects appeared and disappeared abruptly. Witnesses described experiences that blended physical observation with altered states of perception. Rather than concluding that advanced spacecraft were darting between planets, these researchers suggested that the phenomenon might reflect interactions with a parallel realm, one overlapping ours in subtle ways. It is important to approach this calmly. The interdimensional hypothesis remains speculative. It has not been validated by controlled experiments. It is a conceptual framework, not an established scientific theory. Yet it connects intriguingly with the physics we've explored. If extra dimensions exist, curled beyond our perception, then in principle, regions of spacetime could be adjacent in ways we do not intuitively grasp. If wormholes or geometric folds were possible under rare conditions, then brief intersections between regions might occur. Again, possibility does not imply frequency. Let us consider some modern cases often discussed in public discourse. In recent years, several videos recorded by military aircraft have been released. These include infrared footage showing unidentified objects moving against the sky. The recordings, sometimes referred to by informal names based on their appearance, have sparked debate among scientists and the public alike. In these cases, trained pilots described objects accelerating rapidly or maintaining position against strong winds. Subsequent analysis has offered conventional explanations for some aspects of the footage: optical effects, perspective compression, sensor tracking behavior. The objects may not have moved as dramatically as initially perceived once camera angles and relative motion are accounted for. Yet the broader conversation revealed something important. The boundary between known and unknown remains active. Some have speculated that if an object could manipulate local space-time geometry, compressing space in front of it and expanding space behind, it might appear to accelerate without experiencing internal stress. This concept, explored theoretically in studies of warp metrics, would involve shaping the geometry of space rather than pushing through it. However, such models require immense energy densities and forms of matter not known to exist in practical quantities. So once again, we find ourselves balancing curiosity with constraint. There is also a sociological dimension worth noting. When radar systems were upgraded in certain military contexts, reports of unidentified objects increased. This may reflect improved detection sensitivity rather than an actual rise in anomalous activity. Technology changes perception. Perception shapes interpretation. Human cognition is deeply responsive to context. When cultural narratives about visitors or hidden dimensions circulate widely, ambiguous stimuli may be interpreted through those lenses. Psychologists have long studied how expectation influences observation. Under uncertainty, the mind fills gaps with available frameworks. But here is where the interdimensional idea remains intriguing in a quiet way. If anomalies were ever to arise from structural features of space-time, they might not resemble fleets of craft arriving from distant stars. They might appear intermittent, contextual, difficult to categorize. They might involve not only motion in space, but altered perception of time or location. Some witnesses describe objects appearing to blink in and out of existence. From a higher dimensional perspective, this could be analogous to a three-dimensional sphere passing through a two-dimensional plane. The plane dwellers would see a circle appear, grow, shrink, and vanish as the sphere intersects their world. This analogy does not confirm that such events are occurring. It simply illustrates how limited dimensional perception can distort interpretation. There's also the concept of inertia revisited in this context. If a hypothetical object were partially embedded in another geometric layer, its motion might not follow the same inertial paths as objects fully constrained to our spacetime. From our perspective, acceleration could appear abrupt. From its perspective, it might be smooth. Yet this remains theoretical speculation layered atop uncertain observation. Scientific rigor demands repeatability, controlled measurement, independent verification. To date, no confirmed dataset demonstrates macroscopic objects violating the known laws of motion in ways that require new geometry to explain. Still, the interdimensional hypothesis persists in cultural imagination because it offers a different kind of distance. Instead of light years across space, the distance might be measured in hidden directions, microscopic curls of geometry adjacent to our own. It is, in a sense, a sideways journey rather than a forward one. As we sit with this idea, notice how it harmonizes with earlier themes. Extra dimensions suggest adjacency beyond perception. Wormholes suggest connectivity beyond surface distance. Phase transitions suggest structural shifts rather than tears. The interdimensional hypothesis gathers these strands into a single image, reality layered, occasionally intersecting, but mostly separate. Whether that image reflects physical truth remains uncertain, but it does something valuable. It reframes mystery not as invasion from the stars, but as complexity within structure. And complexity, as we have seen, is something the universe already possesses in abundance. So far, we've explored geometry, curvature, and speculative bridges in space-time. We've remained largely in the realm of physics. But there is another class of experiences that often enters conversations about doors between worlds. Experiences that occur not in the sky, but in the mind. Stories of apparitions, moments of déjà vu, collective false memories, near-death visions of light and passage. If we're asking whether boundaries between realities might exist, it is important to examine these reports calmly and respectfully. We begin, as science always does, with the brain. Consider sleep paralysis. During rapid eye movement sleep, the stage when dreams are most vivid, the brain temporarily inhibits most muscle movement. This prevents us from physically acting out our dreams. Occasionally, however, a person awakens before this paralysis has fully lifted. The mind becomes alert while the body remains immobile. In that state, the boundary between dreaming and waking can blur. The brain, still partially immersed in dream imagery, may project shapes or figures into the room. A presence may be felt, a pressure on the chest, a shadow at the edge of vision. Across cultures, these experiences have been interpreted in many ways: night spirits, visitors, entities. Yet when studied under controlled conditions, sleep paralysis reveals consistent neurological patterns. The experience arises from the overlap between dream imagery and waking awareness. The explanation does not diminish the intensity of the event, it simply grounds it in physiology. Next, consider déjà vu. That fleeting sensation that a moment has happened before, a conversation that feels rehearsed, a place that feels strangely familiar. Neurologically, déjà vu appears to involve small mismatches in memory processing. The brain briefly misclassifies a present perception as a stored memory. The feeling of familiarity emerges without a clear source. In rare medical cases involving stimulation of specific brain regions, patients report artificially induced déjà vu sensations. This suggests that the experience is tied to the mechanisms by which memory is encoded and retrieved. Again, the explanation is internal. Then there is what has come to be called the Mandela Effect, the phenomenon where groups of people recall events or details differently from historical records. Some remember brand logos spelled one way when they were spelled another. Some recall public events occurring differently. psychology offers a well-studied explanation. Memory is reconstructive. It is not a perfect recording device. Each time we recall an event, we rebuild it from fragments, influenced by suggestion, expectation, and social reinforcement. When large groups share similar cultural inputs, similar memory distortions can arise. This does not require shifting timelines. It requires shared cognitive patterns. Near-death experiences present another profound category. Individuals who come close to death sometimes report moving through tunnels of light, encountering deceased relatives, or experiencing a panoramic review of their lives. These accounts are deeply meaningful to those who experience them. From a medical perspective, near-death experiences often occur under conditions of extreme stress, oxygen deprivation, or altered brain chemistry. The visual cortex may produce tunnel-like imagery as peripheral vision fades. Neurochemical surges may generate feelings of peace or detachment. Studies have shown that similar experiences can be induced in laboratory settings through controlled stimulation or pharmacological means. This suggests that the core features of near-death narratives arise from brain processes under extreme conditions. Now, having grounded these phenomena in neuroscience, we may gently widen the frame. If consciousness is an emergent property of neural activity, then unusual neural states produce unusual experiences. That is the conservative explanation. However, some have wondered whether altered states might occasionally coincide with altered perception of deeper structure. This is not a claim, it is a speculation. If space-time possesses layers beyond our direct access, and if consciousness is sensitive to subtle patterns in sensory input, then moments when perception becomes unstable might create the impression of crossing boundaries. Notice the language carefully. Impression, not proof. The human brain is exquisitely tuned to detect patterns. It can also detect patterns where none exist. In evolutionary terms, false positives are often safer than missed threats. So when people describe feeling that reality is glitched, or that time briefly folded, the most parsimonious explanation lies within cognitive processing. And yet, the metaphor of a boundary glitch remains compelling. Because we've already seen that physics contains boundaries, event horizons, phase transitions, symmetry breakings. But these boundaries operate at cosmic or subatomic scales, not at the level of living rooms and hospital beds. There is currently no empirical evidence that sleep paralysis or déjà vu correspond to structural changes in space-time. The responsible position is one of layered interpretation. First layer, brain and physiology. Second layer, psychology and social influence. Third layer, philosophical speculation. Never reverse the order. As we rest with these ideas tonight, it is helpful to recognize something comforting. The mind is capable of generating profound experiences without requiring reality itself to fracture. Dreams can feel more real than waking life. Memories can shimmer with emotion decades after they occur. The brain is not a passive camera. It is an active storyteller. If doors between dimensions exist, they would not likely announce themselves through subjective perception alone. They would produce measurable, reproducible anomalies in physical systems. Until such evidence appears, paranormal experiences remain powerful examples of how rich and complex human consciousness truly is. Not evidence of cracks in reality, but evidence of the depth of our inner world. And sometimes the inner world is vast enough to feel like a universe of its own. So far, the anomalies we've explored have lived either in the sky or in the mind. Now we turn to the landscape itself. Throughout history, certain places have gathered reputations. Stories cling to them. They become thresholds in folklore, locations where reality feels thinner, where something might pass through. Let us approach these places the way we've approached everything else, calmly, layer by layer. The Bermuda Triangle is perhaps the most famous. This region of the Atlantic Ocean, roughly bounded by Miami, Bermuda, and Puerto Rico, has been associated with disappearances of ships and aircraft. Stories of lost flights, vanishing vessels, and malfunctioning instruments have circulated for decades. Yet when examined statistically, the number of incidents in this region does not significantly exceed those in other heavily travelled areas of ocean. The triangle lies along busy shipping lanes and common flight paths. The weather in the region can change rapidly. Sudden storms, powerful currents like the Gulf Stream, and human error all contribute to navigational hazards. Magnetic variation in the area, where true north and magnetic north align in unusual ways, has sometimes been cited as mysterious. But magnetic variation occurs in many places across the globe and is well understood within geophysics. No verified evidence indicates that ships are slipping into other dimensions. What we see instead is a region of challenging conditions amplified by narrative. Now consider Sedona, Arizona. Sedona is known for its red rock formations and striking geological beauty. It has also become associated with so-called vortex sites, locations where visitors report heightened energy, emotional shifts, or spiritual experiences. From a geological perspective, Sedona's rock formations are rich in iron oxide, giving them their distinctive colour. The landscape is dramatic, with sweeping vistas and layered sandstone shaped by erosion over millions of years. Psychologically, breathtaking scenery can induce altered states of awareness. When humans encounter vast natural beauty, the brain responds with feelings of awe. Awe can heighten perception, intensify emotion, and create a sense of presence. Visitors primed by cultural narratives may interpret these sensations as energy fields or portals, but geology provides no evidence of space-time anomalies in Sedona's rock layers. The stones are ancient, the magnetism is ordinary, the awe is real, but it arises within the human nervous system. Next, we travel to England. Stonehenge stands in quiet symmetry on the Salisbury Plain. Massive stones arranged in circular patterns, aligned with the rising and setting of the sun during solstices. To ancient observers, the precision of these alignments must have felt extraordinary. Even today, watching the sun rise between the stones during the summer solstice can feel like witnessing something beyond the everyday. But the astronomical alignment is not supernatural. It reflects careful observation and architectural planning by Neolithic builders. The monument tracks the sun's position on the horizon across the year. In other words, it marks time, and places that mark time often feel like thresholds, moments where cycles turn and seasons shift. Finally, there is Aramumuru in Peru, sometimes called the Gate of the Gods. Carved into rock, the site resembles a doorway, complete with a central indentation. Local legends speak of priests passing through into other realms. Archaeologists, however, interpret the site as a ritual carving, perhaps symbolic, perhaps unfinished. There is no evidence of physical anomalies associated with it, and yet, standing before a rock face shaped like a door, it is difficult not to imagine passage. This brings us to something gentle but profound. Humans are storytellers. When we encounter unusual landscapes, triangles of ocean where storms gather, red rocks glowing at sunset, ancient stones aligned with the sun, carvings shaped like portals, we naturally weave narrative around them. Thresholds are powerful symbols in mythology. Caves, arches, bridges, mountain passes, all represent transition. Our minds are drawn to boundaries. In physics, boundaries are mathematical constructs. Event horizons, phase transitions, symmetry breakings. In key culture, boundaries become sacred sites. There is no shame in this. It is part of how meaning is made. But we must distinguish between metaphorical doors and geometric ones. If space-time ever formed a portal between universes, It would not preferentially choose scenic desert formations or historically significant monuments. It would arise from extreme curvature or rare energetic conditions, not from picturesque landscapes. And yet, these places endure in imagination because they mark something real. They mark the edge of understanding. When ancient builders aligned stones with the sun, they were engaging in cosmology. When sailors vanished in storms, their loss felt inexplicable before meteorology matured. When visitors feel awe at a canyon's edge, the intensity of perception can blur ordinary boundaries. These experiences feel liminal, on the threshold between known and unknown. Perhaps that is the deeper truth. The idea of portals says more about human longing than about geological anomalies. We long for passage, for hidden rooms, for unseen layers beyond the visible horizon. Physics does not currently confirm that specific earthly sites function as dimensional gateways, but it does confirm that the universe is structured in ways more intricate than everyday intuition suggests, and so these landscapes remain powerful, not as cracks in space-time, but as mirrors reflecting our curiosity. They are not doors in the geometric sense. They are doors in the symbolic sense, and symbols too shape how we explore reality. After wandering through portals, anomalies, and symbolic thresholds, it may feel grounding to return to something solid. If there are doors between universes, they remain unconfirmed. But there is one kind of journey we know is possible in principle: travel through ordinary space, not sideways through hidden dimensions, forward, slowly, across the vast distances between stars. The nearest star beyond our sun lies a little over 4 light-years away. A light-year is simply the distance light travels in 1 year. Light moves at roughly 300,000 kilometers per second, so fast that it can circle the Earth several times in a single second. And yet, even at that speed, reaching the nearest star would take more than 4 years. Our fastest spacecraft would take tens of thousands of years. This immediately reveals the scale of the challenge. Interstellar travel is not forbidden by physics, but it is constrained by energy. One proposal involves light sails. Instead of carrying fuel, a spacecraft could deploy a vast, ultra-thin reflective sail. Powerful lasers or sunlight could push against the sail, transferring momentum. Over time, the craft could accelerate to a significant fraction of the speed of light. This idea has been studied seriously. The physics is straightforward. Light carries momentum, even though it has no mass. When light reflects off a surface, it imparts a tiny push. The difficulty lies in engineering. The sail must be extremely lightweight yet durable. The laser array required to accelerate it would be enormous, and decelerating at the destination presents an additional challenge. Another concept involves antimatter. When matter and antimatter meet, they annihilate each other, converting their mass into energy according to Einstein's famous relation. In words, that relation states that mass can be transformed into energy, with the amount determined by the speed of light squared. Because the speed of light is such a large number, even a small amount of mass corresponds to an enormous amount of energy. Antimatter propulsion would, in theory, offer extraordinary efficiency. But there is a problem. Antimatter is extremely difficult to produce and store. In laboratory conditions, tiny quantities are created in particle accelerators. These amounts are microscopic. Storing antimatter safely requires isolating it from ordinary matter using magnetic traps. Scaling this up to spacecraft levels is currently beyond our technological reach. So while the energy potential is immense, the engineering remains daunting. There's also a quieter, slower approach: generation ships. Instead of accelerating to near-light speed, a spacecraft could travel at modest velocities, carrying an entire community. The journey might take centuries. The original crew would not live to see the destination. Their descendants would. This approach shifts the problem from physics to sociology. How do you sustain a stable society in isolation for generations? How do you maintain knowledge, governance, purpose? What happens if cultural drift occurs, if the descendants forget why they are travelling? Interstellar travel is not only about propulsion, it is about psychology. Even within our own solar system, astronauts experience isolation and confinement. Long-duration missions require careful attention to mental health. Now imagine multiplying that by decades, then centuries. There is also the question of relativistic travel. As objects approach the speed of light, time for those objects slows relative to stationary observers. This effect has been measured with extraordinary precision using atomic clocks on aircraft and satellites. In simple terms, if you travel very fast and return, less time will have passed for you than for those who remained behind. This is sometimes described as time dilation. It is not science fiction. It is a measured property of space-time. However, reaching speeds where this effect becomes dramatic requires enormous energy. Accelerating a spacecraft to even a small fraction of light speed demands more energy than humanity currently produces annually. So we face a choice. We can imagine shortcuts, wormholes, warp drives, portals between dimensions, or we can confront the long road. The long road is slow, it is difficult, but it respects the geometry we know. In a sense, interstellar travel becomes a mirror for our discussion of doors. If no shortcut exists, then exploration demands patience. It demands engineering ingenuity rather than geometric miracles. And this patience reveals something important. Even without portals, the universe is accessible, just not quickly. The stars are not unreachable, they are simply far. And perhaps there is something quietly beautiful in that. A civilization that learns to travel between stars would have mastered not only propulsion, but sustainability, cooperation, and long-term thinking. It would have learned to live with distance rather than bypass it. As we move forward in our exploration, this distinction matters, because if doors between dimensions exist, they would represent extraordinary exceptions to the rules of energy and motion. Interstellar travel reminds us of those rules. Distance requires time, acceleration requires energy, inertia resists change. These are not obstacles placed to frustrate us. They are features of a coherent universe, and coherence is what makes science possible. So before we step into time travel and the bending of chronology itself, we pause here, at the edge of our solar system, recognizing that even the ordinary path through space is vast enough to inspire wonder. The long way around may be slow, but it is real. Distance stretches the imagination, but time stretches it even further. When people speak of doors between dimensions, they often imagine not only moving across space, but stepping across time, visiting the past, seeing the future, slipping between moments as though they were rooms along a corridor. Before exploring speculation, we begin with something solid. Time travel to the future is real, not in dramatic leaps, not in sudden jumps, but in measurable, repeatable ways. According to Einstein's theory of relativity, time does not pass at the same rate for everyone. The rate at which time flows depends on motion and gravity. If you travel very fast relative to someone at rest, your clock runs more slowly than theirs. If you sit in a strong gravitational field, such as near a massive planet, your clock also runs more slowly compared to someone farther away. This effect has been confirmed through experiment. Atomic clocks placed on airplanes tick slightly differently from identical clocks left on the ground. Satellites orbiting Earth experience both motion-based and gravity-based time shifts. Engineers must correct for these differences to maintain accurate global positioning systems. In simple words, motion and gravity bend not only space, but time. If you were able to travel near the speed of light and return, you would have aged less than those who stayed behind. You would step into their future. This is not fiction. It is built into the geometry of space-time. But what about travelling backward? Here, the ground becomes less firm. Certain solutions to the equations of general relativity allow for what are called closed time-like paths that loop back into earlier moments. These solutions involve extreme conditions, rapidly rotating universes, infinitely long cylinders of dense matter, or exotic space-time geometries. While mathematically consistent under specific assumptions, these scenarios require physical conditions that may not exist in reality. Even if such paths were possible, they introduce paradoxes. The most famous is sometimes called the grandfather paradox. If you travel to the past and prevent your own ancestor from meeting your grandmother, how could you have been born to travel back in the first place? To address such contradictions, physicists have proposed various ideas. One proposal suggests that the universe enforces consistency. In this view, events along a time loop must align in a way that prevents logical contradictions. You could travel to the past, but you would be unable to alter events in ways that break causal coherence. In gentler language, the story must remain self-consistent. If you appear in the past, your actions were always part of that past. Another idea suggests that travelling to the past might create a branching timeline, rather than altering your original one. In that case, you would not change your own history. You would step into a parallel version of events. Notice how this returns us to the multiverse discussion. Time travel, in some interpretations, becomes a sideways movement between branches rather than a reversal of a single line. However, there is currently no experimental evidence that macroscopic backward time travel is possible. Relativity allows forward time dilation. It does not easily allow safe return to yesterday. There is also something philosophically subtle here. We often imagine time as a flowing river, always moving forward, carrying us along. But relativity encourages a different image. In space-time diagrams, past, present, and future coexist within a four-dimensional structure. The now we experience is simply a slice through that structure. Some physicists describe this as the block universe view. In that picture, all moments exist within the geometry of space-time. We move through them along our world line, the path we trace through time. If that is true, then time travel would not involve rewinding a tape. It would involve navigating the geometry of the block, but again, navigation requires structure. And while forward time dilation is confirmed, no known technology allows backward traversal of a world line without extreme and possibly unphysical conditions. It is also important to consider energy. Accelerating an object to speeds approaching that of light requires ever-increasing energy. As speed increases, inertia increases as well. The closer you approach light speed, the more energy is required for each additional increment of speed. In words, nature resists pushing massive objects to the ultimate speed limit. Time travel to the future through motion is possible, but expensive. In energy, time travel to the past remains speculative and paradox-laden. So where does this leave the idea of doors between times? If space-time can curve and fold, perhaps certain geometric configurations might allow unusual connections between moments. Wormholes, if they could be stabilized and manipulated, have been proposed as potential time machines in theoretical studies. But these proposals depend on exotic energy conditions and precise engineering far beyond current capability. And even then, self-consistency constraints might forbid paradoxical alterations. As we rest with these ideas, something gentle emerges. Time is not as rigid as it feels. It stretches, it dilates, it bends under gravity. But it is not chaotic. It does not casually unravel. The laws governing time are among the most precisely tested in physics. If doors through time exist, they would not be accidents. They would be rare geometric features requiring extraordinary conditions. For now, the only confirmed time travelers are astronauts moving a fraction of a second into Earth's future. And perhaps that is enough to remind us that reality is already stranger than intuition, without requiring dramatic leaps into yesterday. Whenever physics opens even a small window, stories rush toward it. Time dilation is real. Relativity bends clocks. The geometry of space-time is flexible, and in that flexibility, imagination finds space to wander. Over the years, a number of stories have circulated. Stories of visitors from the future, mysterious travelers with impossible passports, devices capable of viewing the past. These stories are fascinating. They reveal how deeply the idea of moving through time captures the human mind. Let us explore them gently, without dismissal and without endorsement. In the early 2000s, an individual using the name John Titor appeared on internet forums claiming to be a time traveller from the year 2036. He described a future shaped by civil conflict and technological shifts. He claimed to have travelled back to retrieve a specific type of computer necessary in his timeline. The narrative included technical details, references to rotating black holes and gravitational distortion, phrased in ways that sounded scientific. For a time, the story attracted serious attention, yet no verifiable evidence accompanied the claims. Predictions did not unfold as described. No physical artifacts were presented for independent testing. Over time, most observers concluded that the account was a work of fiction, perhaps collaborative, perhaps individual. What remains interesting is not the truth of the claim but its structure. It borrowed language from relativity. It invoked rotating black holes, objects known in physics as Kerr black holes. It referenced gravitational effects in ways that sounded plausible to those familiar with scientific vocabulary. The story demonstrates how scientific concepts can lend credibility to narrative. Another tale often repeated is that of the man from Taurid. According to the legend, a traveller arrived at an airport claiming to be from a country that did not exist. He presented documents from a place called Taurid, located between France and Spain. When authorities investigated, no such nation appeared on any map. The story concludes with the man vanishing mysteriously from custody. However, careful research suggests that the tale likely arose from misreported or embellished events involving a traveller from Andorra, a small country situated between France and Spain. The name Tord may have been a distortion of Taurid or similar phonetic confusion. Memory and repetition transform ambiguity into legend. Then there is the chronovisor, a device allegedly built by a group of scientists and religious figures to view past events. According to the story, it allowed observers to see scenes from ancient history, including events from classical Rome. The narrative blends technological mystique with spiritual intrigue, yet no verified documentation of such a device exists. No reproducible demonstrations were ever presented. The story persists primarily through secondary accounts and speculation. Now let us consider something slightly different. Ronald Mallet, a physicist, has proposed a theoretical model involving circulating laser beams designed to twist space-time in a manner that might allow limited forms of backward time travel. His work is grounded in real mathematics derived from general relativity. The concept involves creating a circulating light field intense enough to influence space-time curvature. In words, the idea is that energy in motion can affect geometry. If light was circulated in a closed loop with sufficient intensity, it might produce a subtle twisting of space-time around it. However, even sympathetic physicists note that the energy densities required would be extraordinary. The practical obstacles are immense. Moreover, the model does not allow travel to times before the machine's activation. It would only permit limited loops under highly constrained conditions, if it works at all. Mallett's proposal illustrates an important distinction. It is one thing to claim a functioning time machine exists in secret. It is another to explore mathematically how space-time might behave under extreme conditions, even if engineering remains infeasible. The former belongs to legend. The latter belongs to speculative but serious theoretical inquiry. Across all these stories, a pattern emerges. They rely on the language of physics, rotating black holes, gravitational distortion, temporal displacement, laser-induced curvature. But language alone does not establish reality. Science requires independent verification, reproducible evidence, predictions that withstand scrutiny. To date, no confirmed case demonstrates that a human has travelled backward in time, and yet these stories endure. Why? Because time feels like the most intimate dimension. We live inside it. We age with it. We remember backward and anticipate forward. The idea of stepping outside that flow feels transformative. In myth, time travel often functions as moral reflection. A traveller returns to correct mistakes, to warn others, to glimpse consequences. In physics, time is part of geometry. The difference matters. One speaks to longing, the other to measurement. As we settle this session gently, notice something reassuring. Even without backward time travel, the universe already allows us to see into the past. When we look at distant stars, we see light that left them years, centuries, even millions of years ago. Telescopes are natural time machines in one direction. We cannot visit yesterday, but we can observe ancient light. And perhaps that is a quieter kind of door, one built into the finite speed of light itself. Stories of travellers may continue to circulate. They may entertain, inspire, and provoke curiosity. But as of now, the only confirmed time travellers are photons crossing cosmic distances, and they travel faithfully, not through secret portals, but through the steady geometry of space-time. So far, we have asked whether doors might exist. We have asked whether motion, perception, or time could bend in unusual ways. Now we turn to a softer question. If there are other regions of reality, other universes with slightly different constants, or distant planets under unfamiliar skies, what might life look like there? To answer this gently, we begin with what shapes life here. Life on Earth is shaped by gravity, chemistry, temperature, and energy flow. Gravity pulls downward with steady force. Chemistry is governed by the interactions of atoms, especially carbon, which forms stable and versatile bonds. Water acts as a solvent, enabling complex molecules to interact. Change these conditions, and life would change too. Imagine a world where gravity is significantly stronger. On such a planet, tall trees might be rare, creatures might be compact and low to the ground, bones would need to be thicker, muscles stronger relative to size, evolution would favour sturdiness over height. In contrast, on a world with weaker gravity, life might stretch upward. Organisms could grow taller and thinner, wings might become more efficient, movement could feel lighter, more buoyant. These are not fantasies, they are extensions of biomechanics. Now consider temperature. On Earth, life thrives within a narrow range of heat. But extremophiles, organisms that live in boiling hot springs or deep beneath polar ice, show us that biology can adapt beyond what once seemed possible. If a planet were warmer overall, perhaps oceans might be thicker with dissolved minerals. If colder, life might rely on antifreeze-like proteins to prevent cellular damage. Chemistry also matters deeply. Carbon is uniquely suited for building complex molecules because it can form 4 stable bonds, but some scientists have speculated about silicon-based life, since silicon sits beneath carbon on the periodic table and shares certain bonding properties. Silicon-based life remains hypothetical. Silicon compounds tend to be less flexible than carbon-based ones in Earth-like conditions, but on planets with different temperatures or pressures, silicon chemistry might behave differently. Notice how we remain grounded. Speculation is allowed, but within chemical plausibility. Now imagine worlds orbiting twin stars. 2 suns in the sky would create complex cycles of light and shadow. Seasons might be unpredictable. Organisms might evolve internal clocks more adaptable than ours. Or imagine a planet covered in thick clouds of methane, with lakes composed not of water, but of liquid hydrocarbons. In our own solar system, Saturn's moon Titan contains lakes of methane and ethane. Though temperatures there are extremely cold, some researchers have explored whether exotic forms of chemistry could occur in such environments. We have no evidence of life there, but the fact that chemistry can occur in varied solvents reminds us that water, while common here, may not be universal. Now widen the lens further. If we entertain the possibility of universes with slightly different physical constants, the picture becomes more complex. If gravity was stronger everywhere, stars might burn more quickly. If weaker, star formation might be rare. The balance between the electromagnetic force and gravity determines how atoms hold together and how stars ignite. Tiny shifts in these values could produce universes inhospitable to complex structures. This observation is sometimes described as fine-tuning. The constants of our universe appear to lie within a narrow range that permits long-lived stars and stable chemistry. Whether this is coincidence, necessity, or evidence of a broader multiverse remains debated. But if multiple universes exist, each with slightly different parameters, then some might allow forms of life radically different from ours. Not glowing beings of pure energy, but organisms adapted to different balances of force. For example, in a dense atmosphere with heavy gravity, life might evolve in gelatinous forms, distributed masses rather than rigid skeletons. In environments with high radiation, organisms might incorporate protective minerals into their structure. In metallic seas, if such a chemistry were stable, life would need entirely different metabolic pathways. And yet, certain constraints likely remain universal. Thermodynamics governs energy flow. Systems require gradients, differences in temperature or chemical potential, to drive metabolism. Without energy gradients, complexity struggles to arise. Information storage requires stability. Whether encoded in DNA or some alternative molecule, replication must occur with sufficient fidelity to allow evolution. So while imagination may stretch, physics still frames the possibilities. Now, what of intelligence? Intelligence evolves under environmental pressures. On Earth, it emerged in species that benefited from cooperation, tool use, and adaptability. In a high-gravity world, intelligence might arise in compact subterranean organisms, in low-gravity environments, perhaps in aerial species navigating vast skies. If additional dimensions were accessible to some form of life, perception might extend beyond what we consider ordinary space. But such speculation quickly moves beyond current evidence. It is wiser to proceed carefully. Life adapts to environment. Environment is defined by physical law, and physical law appears remarkably consistent across the observable universe. If doors between universes exist, and if those universes possess different constants, then stepping through such a door might mean entering a realm where chemistry itself differs. An organism evolved under one set of constants might not survive under another. This brings an unexpected humility to the idea of portals. Even if passage were possible, compatibility is not guaranteed. As we reflect tonight, imagine distant worlds, not as fantasy kingdoms, but as laboratories shaped by gravity, temperature, and chemistry. Life elsewhere may be stranger than fiction, but it would still be rooted in structure. And structure, as we have seen, is what makes doors meaningful in the first place. Because a door only matters if something can pass through, and something can only pass through if it is built to endure what lies beyond. So far, we have asked what doors might be made of: geometry, curvature, energy, chemistry. But there is another layer of the question, quieter, more intimate. If there are deeper structures to reality, if space-time possesses hidden directions or parallel branches, could consciousness be the first place we notice subtle shifts? We must tread carefully here. Consciousness is not fully understood. Neuroscience has mapped regions associated with memory, emotion, perception, and self-awareness. Brain imaging reveals networks that activate when we reflect on ourselves or imagine the future. Yet no single equation captures subjective experience. We know that consciousness correlates with neural activity. When specific regions are damaged, aspects of awareness change. When anesthesia alters brain chemistry, consciousness fades. These observations strongly support the idea that awareness arises from physical processes in the brain. This is the foundation. But within that foundation, there are open questions about how subjective experience emerges from electrical and chemical signals. Some philosophers describe consciousness as an interface, a way the brain models the world in simplified terms to guide survival. Imagine a computer desktop. The icons you see are not literal representations of circuits and voltages inside the machine. They are simplified symbols that allow you to interact efficiently with complex processes. In a similar way, perception may not show us reality as it is, but as it is useful. Now consider dreams. When you dream, your brain constructs environments, characters, and narratives without external input. Entire landscapes unfold behind closed eyelids. You may fly, fall, converse, or revisit memories. The neural activity during dreaming is measurable. It involves activation of visual areas, emotional centers, and memory circuits, often with reduced activity in regions responsible for critical reasoning. In other words, dreams arise from internal processing. Yet some people have wondered, quietly, whether dreams might also reflect something more. Not proof of parallel lives, not evidence of dimensional travel, but perhaps glimpses of the brain exploring possible realities. In cognitive science, the brain is sometimes described as a prediction engine. It constantly generates models of the world, testing them against incoming sensory data. During dreaming, the predictive machinery runs without constraint from sensory input. It explores possibilities. Some have poetically imagined that if multiple branches of reality exist, as suggested in certain interpretations of quantum mechanics, then dreams might feel like rehearsals of alternate paths. This is metaphor, not measurement. There is no empirical evidence that dreams correspond to parallel universes, but the metaphor highlights something interesting. Identity itself is flexible. Consider how different you feel in different contexts. At work, with family, alone in thought. The sense of self shifts subtly with environment and memory. If multiple versions of events were to unfold in a branching multiverse, there would be countless versions of you, each shaped by different choices. From our perspective, we experience a single thread, but philosophically, the idea of alternate selves raises questions about what defines identity. Is it memory continuity, physical continuity, narrative coherence? These are deep questions, explored not only in physics but in philosophy of mind. Now, let us return to the more speculative suggestion. Could consciousness ever detect anomalies in space-time structure? There is currently no evidence that the brain is sensitive to geometric fluctuations beyond ordinary sensory input. Neural processes operate at scales vastly larger than quantum fluctuations. However, some researchers have explored whether quantum processes play a role in consciousness. These theories remain controversial and unproven. The dominant scientific view holds that consciousness emerges from complex classical interactions among neurons. Still, the idea of awareness as an interface remains powerful. If reality is layered, and if perception presents a simplified model, then anomalies, if they ever occurred, might first appear as perceptual irregularities. But here again, caution prevails. Perceptual irregularities are common. Memory lapses, visual distortions, emotional surges. These do not require dimensional shifts to explain, and yet as humans, we often use spatial metaphors to describe inner states. We say we feel disconnected, as if a thread has snapped. We describe moments of clarity as breakthroughs. We speak of crossing a threshold in understanding. Perhaps the language of doors resonates so strongly because consciousness itself feels like a boundary between inner and outer worlds. When someone imagines meeting an alternate version of themselves, it often reflects a confrontation with unrealized possibilities, the person they might have become under different circumstances. In this sense, alternate selves exist psychologically, even if not physically. The brain continuously simulates future scenarios, it constructs counterfactuals, it imagines different outcomes. So when stories of parallel selves circulate, they tap into a natural cognitive function. We are built to imagine branching paths. Whether those branches exist in physical reality is another matter. As we rest here tonight, notice something subtle. The question of doors between dimensions does not only concern stars and black holes, it concerns how we interpret experience. If the universe is layered, and if geometry may contain hidden directions, consciousness remains our only access point to perception. But consciousness is not a flawless instrument. It is adaptive, narrative, and sometimes mistaken. So the responsible stance is gentle curiosity. Some have wondered whether perception could detect deeper structures. Science, for now, finds no evidence that it does, but the fact that we can even pose the question reflects something remarkable. The universe has evolved, at least once, a structure capable of asking whether it has hidden layers, and that structure is us. Up to this point, we've imagined doors as bridges between regions, connections between bubbles, tunnels through curvature, phase transitions in spacetime. But there is another possibility, quieter, stranger, and more inward. What if there is no door to open because we are already inside one? This question arises from what is often called the simulation argument. The core reasoning is surprisingly simple. As computing power advances, it becomes increasingly plausible that a sufficiently advanced civilization could simulate entire environments, perhaps even conscious agents within those environments. If such civilizations create many simulations, then statistically, simulated realities could outnumber original ones. From that perspective, it becomes more likely that any randomly chosen conscious observer is inside a simulation rather than at the base layer of reality. This line of reasoning does not claim that we are simulated. It presents a trilemma. Either advanced civilizations rarely reach technological maturity, or they choose not to run simulations of ancestors, or simulated realities vastly outnumber base ones. It is a philosophical argument, not experimental proof. Now let us soften the image. Instead of imagining code and processes, imagine a stage. On this stage, scenery appears only where the spotlight shines. The rest remains unrendered until attention moves. Some have noticed that quantum mechanics behaves in a way that invites metaphor. At very small scales, particles do not possess definite positions and velocities simultaneously in the way classical objects do. Their behavior is described in terms of probabilities until measured. When an observation occurs, one outcome becomes actualized. This has led some to poetically suggest that reality behaves like a system that resolves detail when observed. But we must tread carefully. Quantum indeterminacy does not imply that consciousness creates reality. It reflects the probabilistic structure of quantum fields. Still, the metaphor persists. If reality operates according to underlying informational rules, perhaps spacetime itself is emergent from deeper layers of information. Some physicists have explored the idea that the universe is fundamentally mathematical, that physical laws arise from abstract structures. Others have examined the holographic principle, which suggests that the information describing a volume of space may be encoded on its boundary. In certain formulations of quantum gravity, space-time emerges from patterns of entanglement, relationships between microscopic degrees of freedom. Notice how these ideas converge. Geometry may not be fundamental, information might be. If so, then a door between dimensions could be a change in informational configuration rather than spatial movement. But let us not leap too quickly. There is currently no empirical evidence that we inhabit a literal computer simulation. The simulation argument is philosophical. It extrapolates from technological trends and probabilistic reasoning. It does not arise from a specific measurement revealing pixelation in spacetime, yet some features of physics intrigue thinkers. The constants of nature appear finely balanced to permit complex structures. If the strength of gravity was slightly different, stars might burn too quickly or fail to ignite. If electromagnetic interactions were stronger or weaker, chemistry might not sustain stable molecules. This apparent fine-tuning has several possible explanations. It could reflect necessity. Perhaps only universes with such parameters allow observers capable of noticing them. It could reflect multiverse selection. Many universes exist with varied constants, and we inhabit one compatible with life. Or, in a more speculative interpretation, constants might resemble adjustable parameters within a deeper framework. But speculation does not equal conclusion. As of now, the constants are measured facts. Their origin remains an open question. If we imagine for a moment that reality is informational at its core, then doors between dimensions might correspond to transitions between informational states, but that remains abstract. More grounded is the observation that our physical theories increasingly describe the universe in terms of fields, probabilities, and information exchange. Whether this implies simulation or simply deeper mathematical structure remains unresolved. It's also worth reflecting on humility. Throughout history, humans have repeatedly discovered that reality is stranger than assumed. The Earth orbits the Sun. Space expands. Time dilates. Particles behave as waves. Each discovery felt destabilizing at first. The simulation hypothesis may be another destabilizing idea, one that challenges intuition but remains unproven. And perhaps the most grounded stance is this. Even if reality were emergent from deeper informational rules, those rules are consistent. They allow stars to shine, atoms to bond, and life to evolve. From within the system, the experience of existence remains meaningful. A door between dimensions, in this view, would not be a physical portal but a shift in description, a deeper layer of explanation. Whether such layers exist beyond current theories is an open question, but asking it reveals something beautiful. The universe is intelligible enough that we can wonder about its foundations, and that wonder itself may be the closest thing to a doorway we can confidently claim. After geometry, after wormholes, after dreams and simulations, We arrive at the quietest and perhaps most human question of all. What would happen if a real door opened? Not a metaphor, not a philosophical possibility, but a measurable, repeatable, undeniable phenomenon. A region of space-time that connects to another domain of reality. The first impact would be scientific. Physics would undergo transformation. The unification of gravity and quantum theory, long sought, might accelerate. Constants could be tested across domains. If a connected region possessed slightly would form around the portal's edge, instruments would be extended cautiously across the boundary. Sensors would measure radiation, pressure, curvature. The discovery would not instantly answer all questions. It would multiply them. Next would come ethical considerations. Who controls access? Is the portal a natural feature, or did human intervention create it? Should it be explored immediately or studied remotely for years? What risks exist in sending biological organisms across? Interdimensional ecology would become a central concern. Even small differences in physical constants could render environments incompatible. Microorganisms from one domain might behave unpredictably in another. Chemical reactions could proceed differently under altered conditions. Strict containment protocols would likely be established. Remote probes might be sent before any human presence. Then there are religious and philosophical consequences. Throughout history, humanity has revised its worldview when confronted with cosmic discoveries. The realization that Earth orbits the Sun reshaped cosmology. The expansion of the universe reshaped our sense of scale. A portal to another realm would challenge notions of uniqueness. It might expand theological interpretations. Some would see it as confirmation of hidden realms long described in sacred texts. Others would reinterpret doctrine to integrate new knowledge. Cultural responses would vary. Geopolitically, tension would arise. Nations would compete for influence over the site. International agreements might form rapidly, recognizing that such a discovery transcends borders. Would the portal be considered a global commons, a strategic asset, a scientific sanctuary? History suggests that cooperation and competition would unfold simultaneously, but perhaps the deepest impact would be psychological. If a stable connection to another universe existed, humanity would confront a mirror of possibility. What if that universe resembled ours but differed subtly? What if its history diverged at some distant branching point? Meeting another intelligent civilization, if one existed across the threshold, would redefine identity. And what if there were no life there? What if the other side were empty? Even that emptiness would speak volumes about the rarity of complexity. There is also a quieter scenario. What if the portal led not to a different universe, but to a distant region of our own, connected through exotic geometry? The revelation would still be profound. Distance would be redefined. Travel would change. But we must temper imagination with realism. All current evidence suggests that if portals exist, they require extreme conditions far beyond everyday environments. The energy scales associated with bending space-time at macroscopic levels are immense, comparable to those found near black holes or in the early universe. No known natural phenomenon on Earth displays such characteristics, so perhaps the opening of a portal would not be sudden or accidental. Perhaps it would require deliberate engineering if possible at all, and if that engineering were ever achieved, the responsibility would be enormous. A door is not only an opportunity, it is a risk. Yet amid these considerations, something gentle emerges. For thousands of years, humans have imagined thresholds, caves leading to other worlds, gates in mountains, stairways to the heavens. Science has replaced myth with measurement, but it has not erased wonder. If a portal were ever confirmed, it would not shatter meaning. It would expand it. The universe would become larger, not less coherent, and perhaps the greatest shift would not be external, but internal. We would know with certainty that reality has layers beyond immediate perception. Curiosity would deepen, humility would grow. But until such a door appears, and none has yet, the most profound doorway available to us remains inquiry itself. We ask questions, we build models, we test boundaries carefully. Perhaps doors are rare, perhaps many anomalies dissolve under scrutiny. Perhaps the geometry of our universe is self-contained, vast but unbroken. Or perhaps somewhere in the depths of space-time folds exist that we have not yet encountered. Whatever the case, the act of wondering is not wasted. It is the quiet force that has carried humanity from myths to mathematics, from speculation to satellite clocks that measure the slowing of time in orbit. Tonight, we have explored possibilities without abandoning discipline. We have let imagination stretch, but not tear. And in that balance, between curiosity and caution, we find something steady. The universe may contain doors, or it may simply contain depth. Either way, we are already standing at the edge of something extraordinary. And sometimes standing at the threshold, calm, observant, patient is enough.